Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should make your brain pause, not with alarm, but with a deep, quiet sense of the universe's intricate design. For as long as humans have looked up at the night sky, for as long as our species has walked this planet, for billions of years before that, one celestial body has presented us with an unwavering, unchanging face. The moon, our constant companion, our silent guardian, always shows us the exact same side. Think about that for a moment. Every single person who has ever lived, from the earliest hominids gazing up in awe to the astronauts who orbited it, has seen the same familiar craters, the same dark Maria, the same patterns etched onto its surface. It's a cosmic steadfastness that defies our everyday experience. We're used to things spinning, tumbling, presenting all their facets. Our own Earth spins on its axis once every 24 hours, giving us day and night, constantly revealing new landscapes to the sun. But the moon, it's different. It performs a quiet, elegant ballet, always keeping one eye fixed on us, its larger partner. It's not a trick of perspective, not an optical illusion. It is a profound physical reality, a testament to forces so subtle and persistent that they have shaped worlds over eons. This isn't just a quirky fact. It's a window into the fundamental interactions that govern the dance of celestial bodies, a whisper of the universe's deep, patient power. And understanding why this happens reveals a universe far more interconnected and dynamic than we often imagine. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's start with a cosmic riddle that's been hanging in the night sky for billions of years, a riddle so fundamental that most of us don't even realize it is a riddle. Why do we only ever see one side of the moon? It feels so natural, so obvious that we rarely question it. The moon is just there, a familiar friend, always presenting the same face. But this apparent stillness, this unwavering presentation of a single hemisphere, is one of the most elegant and profound examples of celestial mechanics at play. It's not that the moon doesn't rotate. In fact, it rotates with exquisite precision. A rotation so perfectly matched to its orbital journey around Earth that it creates this constant single view. This phenomenon is called synchronous rotation, or more commonly tidal locking, and it's a secret shared by many moons throughout our solar system. To truly appreciate this cosmic secret, we first need to clarify a couple of fundamental concepts: rotation and revolution. These terms are often used interchangeably in everyday language, but in astronomy they describe two distinct types of motion, and understanding their difference is key to unraveling the moon's mystery. Imagine yourself standing still in a room. If you spin around on your own axis, completing a full 360-degree turn, that's rotation. The Earth rotates on its axis, giving us day and night. Now, imagine you start walking in a circle around a central object, like a pole in the middle of the room. That movement, orbiting the pole, is revolution. The Earth revolves around the Sun, giving us our year. The Moon, like Earth, does both. It rotates on its own axis, and it revolves around the Earth. The mind-bending part is that for the Moon, these two periods of motion are almost perfectly synchronized. Specifically, the Moon completes one full rotation on its axis in almost precisely the same amount of time it takes to complete one full revolution around the Earth, and that specific duration is approximately 27.3 Earth days. Let's be precise. The Moon's sidereal rotation period, the time it takes to spin once relative to the distant stars, is 27 days, 7 hours, 43 minutes, and 11.5 seconds. Its sidereal orbital period, the time it takes to orbit Earth once relative to the distant stars, is also 27 days, 7 hours, 43 minutes, and 11.5 seconds. The match is virtually exact. This means that as the Moon slowly orbits our planet, it is simultaneously rotating on its own axis at the exact same rate. It's like a dancer on a stage, spinning as they move in a circle, but always keeping their face pointed towards a specific audience member. Now here's where the mental model really needs to solidify. If the Moon didn't rotate at all, what would we see? Imagine a Moon that simply moved around the Earth without spinning. In that scenario, as it moved through its orbit, we would, over the course of one revolution, gradually see all of its surface. Picture a static globe, painted with a face on one side. If you carry that static globe around your head, you'd eventually see the quote "one of the globe." But that's not what happens with our Moon. Because it is rotating, and because that rotation is perfectly timed with its revolution, the face that points towards Earth never changes. Let's visualize this with more precision. Imagine a single point on the Moon's surface, perhaps a prominent crater. As the Moon begins its journey around Earth, this crater is facing us. As the Moon moves a quarter of the way through its orbit, it has also rotated a quarter of the way on its axis, meaning that same crater is still facing us. When it's halfway through its orbit, it has rotated halfway on its axis, and the crater is still pointing our way. This continues for the entire 360-degree orbit and the entire 360-degree rotation. The net effect is that the same hemisphere is perpetually oriented towards Earth. It's a continuous, slow-motion adjustment that keeps our familiar lunar face locked in place. This means that the far side of the Moon is not a dark side. This is a common and understandable misconception. The far side of the Moon receives just as much sunlight as the near side. When the Moon is full from our perspective on Earth, the entire near side is illuminated by the sun. At that same moment, the far side is experiencing its lunar night completely dark. Conversely, when we see a new moon, meaning the near side is dark because it's facing away from the sun, the entire far side is bathed in sunlight. So the far side experiences day and night just like the near side does. It just never turns to face us. The discovery of the far side of the Moon was a monumental achievement in space exploration. For centuries its existence was known in theory due to the synchronous rotation, but it remained unseen by human eyes. It wasn't until October 7th, 1959 that the Soviet Union's Lunar 3 probe took the first photographs of the far side. These images revealed a landscape strikingly different from the near side. The near side is dominated by large, dark plains called maria, which are ancient basaltic lava flows. The far side, in contrast, is heavily cratered and has very few maria. This asymmetry itself is a fascinating puzzle, suggesting different geological histories for the two hemispheres, and it's a detail we'll certainly delve into later. The precision of this synchronous rotation isn't just a quirky coincidence, it's a profound outcome of a fundamental force in the universe: gravity. Over vast timescales, the gravitational interaction between the Earth and the Moon has subtly, but relentlessly, shaped the Moon's rotation until it reached this stable, locked state. It's a process that requires energy dissipation, a gradual slowing down until a perfect equilibrium is achieved. This isn't a phenomenon unique to our Earth-Moon system. Many moons in our solar system are tidally locked to their parent planets, from Jupiter's massive Galilean moons like Io and Europa to Saturn's icy Enceladus. It's a common cosmic consequence of prolonged gravitational interaction. So, while the Moon may appear unchanging to our eyes, it is in fact engaged in a complex, precisely timed dance. It rotates, it revolves, and it does so in such perfect harmony that it maintains a constant gaze upon us. This isn't an illusion of stillness, but rather a testament to a deep, underlying physical process, a process that has taken billions of years to play out. The Moon's quote 4 isn't that it doesn't rotate, but that its rotation is perfectly aligned with its revolution, a delicate balance forged by the invisible hand of gravity. This leads us naturally to the next, even more fundamental question. How did this perfect synchronization come to be? What specific mechanism, what subtle yet powerful force, could possibly orchestrate such a precise celestial ballet over such immense stretches of time? The answer lies in the very forces that bind our Earth and Moon together, forces that are constantly at play, shaping not just the Moon's rotation, but also the very oceans on our planet. It's a story of subtle bulges, gravitational tugs, and the slow, inevitable transfer of energy. A story we'll uncover as we delve into the mesmerizing power of tidal forces. We stand at the precipice of a deeper understanding, don't we? Chapter 1 unveiled the elegant what of our Moon's perpetual face, a cosmic riddle solved by the precise, unwavering rhythm of synchronous rotation. We learned that the far side is not a dark side, and that its geological asymmetry, a landscape of ancient craters, was only revealed to us in 1959. But the true enchantment, the profound how of this celestial ballet, still beckons. How did our Moon, this familiar friend, arrive at such a perfectly synchronized state? What invisible hands orchestrated this cosmic waltz, slowing its spin over eons until its rotation matched its revolution? The answer lies in one of the most fundamental and pervasive forces in the universe: gravity. Not just gravity as a simple pull, but as a differential force, a subtle tug-of-war that stretches and molds celestial bodies. We call these tidal forces, and they are the unsung choreographers of countless moons and planets across the cosmos. Imagine our Moon, in its primordial youth, a molten, rapidly spinning sphere newly formed from the debris of a titanic collision. It likely rotated much faster than it does today, perhaps completing a spin in mere hours, not days. Now, envision Earth, our blue marble, as its much larger and more massive partner in this dance. Earth's gravity, an omnipresent force, doesn't pull equally on all parts of the Moon. It pulls more strongly on the side of the Moon closest to us, and slightly less strongly on the side farthest away. Think of it like this. If you hold a piece of taffy and pull on one end while someone else pulls on the other, the taffy stretches. Earth's gravity acts similarly on the Moon, attempting to stretch it along the line pointing directly at our planet. Because the Moon isn't perfectly rigid, this differential pull creates a slight bulge on both the near and far sides, a tidal bulge. The Moon isn't a perfect sphere, it's ever so slightly elongated like a cosmic football, with one end pointing towards Earth and the other directly away. Now, here's where the magic, or rather the physics, truly begins. In those early days when the Moon spun much faster than its orbital period, these tidal bulges wouldn't stay perfectly aligned with Earth. As the Moon rotated, its internal friction, a subtle, ceaseless grinding within its rocky interior, would cause the bulges to lag slightly behind the direct line to Earth. It's a bit like a car driving through thick mud. The mud resists the movement, creating a drag. Earth's immense gravity, however, is relentlessly trying to pull these bulges back into alignment. This constant, gentle tug on the misaligned bulges creates a torque, a twisting force, on the Moon. Picture Earth's gravity reaching out with an invisible hand, grabbing the leading edge of that tidal bulge and trying to pull it back, to slow the Moon's spin and align it perfectly. This gravitational braking mechanism, known as tidal despinning or tidal braking, is incredibly powerful, precisely because it acts over immense stretches of time. For billions of years, Earth's persistent gravitational torque applied a gentle but unwavering drag on the Moon's rotation. Each slight misalignment of the tidal bulge with Earth's gravitational field resulted in a tiny transfer of rotational energy. Where did that energy go? It wasn't simply lost. It was dissipated as heat within the Moon's interior, a slow internal friction that warmed its ancient core and also transferred into the Moon's orbital energy, pushing it slightly further away from Earth. This process continued relentlessly for eons. The Moon's rotation slowed, inch by agonizing inch, until it reached a critical point, the moment its rotation period perfectly matched its orbital period around Earth. At this precise juncture, the tidal bulges align directly with Earth. There is no longer a significant misalignment for Earth's gravity to tug on, and therefore no net torque to further slow the Moon's spin. The system reaches a state of gravitational equilibrium, a cosmic dance where the partners are perfectly in sync, their movements harmonized by the invisible strings of gravity. This is the elegant, stable state we observe today. Tidal locking. The Moon's rotation rate is now so precisely tuned to its orbital rate that its tidal bulges remain fixed along the Earth-Moon axis. It's a testament to the universe's capacity for self-organization, where chaotic early conditions eventually settle into states of profound stability and order. The Moon, once a rapidly twirling object, has been brought to heel by its larger partner, settling into a rhythm that ensures its unwavering gaze upon us. But the story of tidal forces doesn't end with the Moon. This is a two-way street, a reciprocal relationship between cosmic dancers. Just as Earth's gravity exerted a braking force on the Moon's gravity exerts a similar, though weaker, braking force on Earth. We experience this most dramatically in our ocean tides, but the Moon's pull also creates a tiny, almost imperceptible, body tide. In Earth's solid crust, a slight bulging of our planet itself. Because Earth is still rotating much faster than the Moon orbits, our planet's tidal bulges also lead the Moon's position. The moon's gravity then pulls back on these bulges, creating a torque that subtly, incrementally, slows Earth's rotation. This is why our days are gradually getting longer, by about 2.3 milliseconds per century. It's an almost imperceptible change in our daily lives, yet over geological timescales, it adds up to profound shifts. 400 million years ago, a day on Earth was only about 22 hours long, and there were over 400 days in a year. And there's another fascinating consequence of this cosmic exchange. As the moon steals rotational energy from Earth, it gains orbital energy. This means the moon is slowly, almost imperceptibly moving away from us. Each year our silent guardian drifts about 1.5 inches, 3.8 centimeters, further into the cosmic expanse. It's a slow, graceful retreat, a testament to the conservation of angular momentum within the Earth-Moon system. The energy lost from Earth's spin is transferred to the Moon's orbit, pushing it outward, expanding the radius of its celestial dance. This grand process of tidal locking isn't unique to our Moon. It's a common phenomenon throughout our solar system and we presume across the universe. Many of the moons orbiting the gas giants, Jupiter, Saturn, Uranus and Neptune, are tidally locked to their massive parent planets. Pluto and its largest moon, Charon, are even more intimately locked. They are mutually tidally locked, meaning each always shows the same face to the other. Imagine a pair of dancers, forever gazing into each other's eyes as they spin together across the ballroom of space. So, when we gaze up at the moon tonight, we are not just seeing a familiar face, we are witnessing the culmination of billions of years of gravitational interaction. We are seeing the profound elegance of physics at play, a testament to the relentless shaping power of tidal forces. The moon's unchanging visage is not a static portrait, but a dynamic equilibrium, a perfect synchronization born from eons of cosmic friction and gravitational tugs. It reminds us that even the most constant features of our night sky are participants in an ongoing, intricate ballet, ever-changing, ever-evolving, driven by the fundamental laws that govern the universe. We've now journeyed from the what to the how of the moon's synchronous rotation, unravelling the mechanics behind its steadfast gaze. But the universe, in its infinite wisdom, always holds more questions, more layers of wonder to peel back. What further secrets might this constant companion hold? What mysteries lie beyond its familiar face, waiting for our curious minds to explore? We invite you to continue this journey with us, as we delve deeper into the moon's profound influence and the ongoing discoveries that shape our understanding of its place in our cosmic neighbourhood. We have unravelled the elegant mechanics of synchronous rotation, grasped the relentless power of tidal forces, and traced the moon's journey from a faster spinning satellite to our perfectly synchronized companion. We understand how our familiar friend came to show us only one unwavering face, but the universe, in its infinite wisdom, rarely offers a simple answer without posing a deeper question. If the moon is tidally locked, presenting one hemisphere to us, what does that mean for the other side? What secrets does the hidden face whisper about its past, about its very being, and about the profound influence of our Earth? Let us turn our gaze now to the most striking consequence of this cosmic embrace. The dramatic dichotomy between the moon's near side and its far side. You see, the moon doesn't merely hide a hemisphere. It reveals a startling contrast, a tale of two faces, each etched with the scars and triumphs of billions of years. When Luna 3 first appeared behind the lunar curtain in 1959, the images it sent back were not merely of an unknown landscape, they were of an unexpected one. The far side, we discovered, was not just quote 7, it was profoundly different. Imagine, if you will, the near side we know so well. It is a canvas dominated by vast dark plains, the Luna Maria, Latin for quote 8. These ancient basaltic floodplains, once thought to be oceans by early astronomers, are the frozen remnants of massive volcanic eruptions that occurred billions of years ago. They are relatively smooth, less heavily cratered than the brighter highlands that surround them, giving our moon its distinctive, familiar visage. We see the quote 9, the quote 10, the quote 11, all patterns formed by these dark Maria. Now, picture the far side. Strip away most of those dark, sprawling Maria. Instead, envision a panorama dominated by a relentless tapestry of craters, overlapping and piled upon one another, stretching almost unbroken across the entire hemisphere. It is a landscape of ancient, rugged highlands, fiercely battered by cosmic impacts, a testament to an early violent solar system. Where the near side boasts extensive Maria covering about 30% of its surface, the far side has only sparse small patches, barely covering 1% of its surface. It's as if two different celestial bodies were stitched together, each telling a distinct geological story. Why this stark difference? Why did the lava flow so profusely on one side, yet barely trickle onto the other? This, dear reader, is one of the moon's profound secrets, a riddle intricately tied to its formation, its internal structure, and yes, to the very same gravitational influence of Earth that caused its tidal locking. The prevailing theory points to a fundamental asymmetry in the moon's crust. Scientific data gathered from orbiting spacecraft like NASA's Lunar Reconnaissance Orbiter reveals that the far side's crust is significantly thicker than the near side's, by as much as 10 to 20 miles in places. Think of it as a thicker, more resilient shield. When massive impacts occurred early in the moon's history, puncturing its crust and allowing molten rock from its interior to well up and form Maria, it was simply easier for the lava to break through the thinner crust on the near side. The far side's thicker armour largely resisted these volcanic outflows. But what caused this crustal asymmetry in the first place? Here we delve into the moon's very genesis, into the turbulent aftermath of the giant impact hypothesis, where a Mars-sized body is believed to have collided with the early Earth, ejecting debris that eventually coalesced to form our moon. In this fiery, chaotic beginning, the nascent moon was still hot, its interior molten, its outer layers gradually cooling and solidifying. Our Earth, a much larger and still intensely hot body, would have been a powerful presence right next to it. Some theories suggest that the Earth's intense heat, radiating outward, might have preferentially heated the side of the moon facing it, keeping that side warmer and its crust thinner for longer. Other models proposed that the very tidal forces that locked the moon's rotation could have also influenced the distribution of its internal material, pulling denser, iron-rich material towards the near side, leaving the far side with a thicker, lighter crust. It's a cosmic dance of heat and gravity, sculpting the moon's very foundation. So the visible consequence of tidal locking, the two contrasting faces, is not just a surface phenomenon, It is a window into the moon's deep past, into its violent birth, its slow cooling, and the persistent gravitational embrace of its parent planet. The Earth's invisible hand, we discover, has not only dictated the moon's spin, but has also played a role in shaping its very geology, its internal architecture. And what of that internal architecture? The moon, we know, is not a solid inert rock. It has a complex layered structure, albeit a much simpler one than Earth's. Beneath its asymmetrical crust lies a mantle, and at its heart, a small, partially molten core. While the moon's internal heat engine is far less active than Earth's, it is not entirely dormant. We know, for instance, of moonquakes, faint tremors that ripple through the lunar interior. Some are caused by meteoroid impacts, others by thermal stresses as the moon heats and cools. But a significant portion, the deepest and most regular, are triggered by the relentless gravitational tug of Earth. Think of it. Even now, billions of years after tidal locking, Earth's gravity continues to knead and flex the moon ever so slightly, creating stresses that release as these deep moonquakes. This constant gravitational stress, though subtle, reminds us that the Earth-Moon relationship is not static. It is a dynamic, living system where forces are always at play, subtly shaping and reshaping both bodies. The moon is not merely a passive observer in its tidally locked state. It is an active participant, its interior still responding to the dance. This profound influence extends beyond the moon's crust and core. We have already touched upon the moon's gradual retreat from Earth, inching away at about 1.5 inches, 3.8 centimeters per year, and the corresponding slowing of Earth's rotation, lengthening our days by milliseconds per century. These are not mere scientific curiosities. They are grand, cosmic narratives unfolding over eons. Imagine if we could fast-forward through geological time watching the Earth and Moon evolve. Our once much closer, faster-spinning moon would have appeared significantly larger in the night sky, and our days would have been dramatically shorter. This ongoing, reciprocal tidal interaction paints a picture of an endlessly evolving system. Will the moon eventually drift so far that its gravitational influence becomes negligible? Will Earth's rotation slow to the point where it too becomes tidally locked to the moon, presenting one face to its companion? While the latter is a fascinating thought experiment, the timescales involved are so vast, billions upon billions of years, that our sun will likely expand into a red giant long before such a scenario could fully play out. Yet the very possibility speaks to the ceaseless, transformative power of gravity. The moon, in its elegant, tidally locked state, is more than just a celestial body. It is a cosmic historian, its two contrasting faces telling tales of violent beginnings, molten interiors, and the enduring, shaping power of gravity. It is a testament to the intricate, interconnected nature of our solar system, where every push and pull leaves an indelible mark. And what of the future? What new secrets might the moon, particularly its enigmatic far side, reveal? The far side, shielded from Earth's radio noise, offers an unparalleled radio quiet zone, a pristine environment for building powerful radio telescopes that could listen to the universe with unprecedented clarity, perhaps even detecting faint signals from the universe's earliest moments, the so-called quote 15, before the first stars ignited. It is a frontier not just for lunar geology, but for cosmology itself, as we continue to explore, with new missions planned to land on the far side, to drill into its crust and to establish permanent bases. We are not just seeking to understand our constant companion. We are seeking to understand ourselves, our planet, and our place in the grand tapestry of the cosmos. The moon, our familiar friend, is a silent guardian, a cosmic riddle solved, yet still a source of profound influence and ongoing discoveries, forever beckoning us to understand its deeper secrets and the wondrous, intricate design of the universe. Its unwavering face, always turned toward us, is a constant reminder that even in familiarity, there lies an ocean of untold stories waiting for us to listen. We've journeyed through the moon's intricate past, uncovered the mechanics of its steady rotation, and glimpsed the stark geological contrasts etched upon its familiar near side and its enigmatic far side. We've seen how Earth's gravity, like a patient sculptor, has shaped our lunar companion, slowing its spin and pulling it into a synchronous dance. But here's the truly astonishing revelation. This cosmic ballet, this gravitational embrace, is far from unique to our Earth-Moon system. What we witness with our moon is not an isolated marvel, but a profound testament to a universal law, a pervasive force that orchestrates countless celestial partnerships across the cosmos. Think of it. The same invisible hand of gravity that holds our moon in its unwavering gaze reaches out across the vastness, influencing moons around other planets, and even planets orbiting distant stars. Our moon, with its constant face, serves as a magnificent close-up example of a phenomenon called tidal locking, a state of gravitational equilibrium that is, in fact, incredibly common throughout the universe. It's a recurring theme in the grand symphony of celestial mechanics, a quiet, elegant ballet performed by countless partners, large and small. Let us turn our gaze from our own familiar night sky to the dazzling tapestry of our solar system. We find tidal locking everywhere we look. Consider Pluto and its largest moon, Charon. They are not merely tidally locked to each other, they are mutually tidally locked. Just as Charon always shows the same face to Pluto, Pluto in turn always shows the same face to Charon. Imagine standing on Pluto's surface. Charon would hang motionless in the sky, an eternal sentinel, never rising, never setting. This mutual locking is a testament to their relatively similar masses and their close proximity, a perfectly choreographed duet where neither partner ever turns its back on the other. Then there are the majestic gas giants, Jupiter and Saturn, each a miniature solar system unto itself, orbited by dozens of moons. Almost without exception, their larger inner moons are tidally locked. Jupiter's 4 Galilean moons, Io, Europa, Ganymede and Callisto, those worlds discovered by Galileo that forever changed our understanding of the universe, all exhibit this synchronous rotation. Io, the most volcanically active body in our solar system, is a dramatic example. Its fiery heart is kept molten by the intense tidal forces exerted by Jupiter and the gravitational tugs from its sister moons Europa and Ganymede. These forces perpetually stretch and squeeze Io, generating immense internal friction and heat, a violent consequence of being trapped in a gravitational grip while also being pulled in other directions. But even amidst this internal turmoil, Io presents the same face to Jupiter, a constant fiery visage. Saturn, with its breathtaking rings, also hosts a retinue of tidally locked moons. Titan, its largest and most intriguing moon, shrouded in a thick atmosphere, is tidally locked. Enceladus, with its cryovolcanoes spewing plumes of water ice into space, is also tidally locked. These moons, each a world of wonder, demonstrate the persistent, subtle work of gravity over eons, patiently nudging, slowing, and ultimately aligning their rotations until they reach that perfect synchronous rhythm. How does this persistent universal process unfold? Let us revisit the fundamental mechanics, perhaps with a fresh perspective. Imagine a celestial body like our moon in its youth, spinning faster than it orbits its larger partner. As we've discussed, the larger body's gravity isn't uniform across the smaller one. It pulls more strongly on the side facing it and less strongly on the side farthest away. This differential pull stretches the smaller body, creating those familiar tidal bulges, one facing the larger body and one on the opposite side. Now picture these bulges. If the moon is spinning faster than it orbits, these bulges are constantly being pulled ahead of the direct line between the two bodies. The larger planet's gravity then exerts a powerful, persistent torque on these misaligned bulges. Think of it like a gentle but unyielding hand trying to twist a spinning top. The gravitational pull on the bulge closest to the planet tries to pull it back, to align it directly with the planet. This constant tug-of-war acts as a brake, continuously draining rotational energy from the moon. Where does this energy go? It's dissipated primarily as heat, through friction within the moon's interior, the very flexing and stretching of its rock and mantle. Over millions, even billions of years, this steady braking action gradually slows the moon's rotation. It's a cosmic dance where the larger partner subtly, but inexorably guides the smaller one, teaching it a slower, more deliberate turn. The process continues until the moon's rotation period exactly matches its orbital period. At this quote 16, the tidal bulges are perfectly aligned with the gravitational pull of the larger body. There is no longer any net torque to speed up or slow down the rotation. The system achieves a state of stable equilibrium, a gravitational embrace where the moon's rotation is perfectly synchronized with its orbit. It's a moment of profound cosmic peace, a silent agreement between two celestial bodies. Our moon reached this equilibrium billions of years ago, and it has remained in this stable, tidally locked state ever since, presenting its unwavering face to us, its constant companion. This understanding of tidal locking isn't just a fascinating detail about our moon or the moons of our solar system. It has profound implications when we turn our gaze beyond to the countless exoplanets now being discovered around other stars. As we search for life beyond Earth, we often look for planets in the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Many of these potentially habitable exoplanets orbit red dwarf stars, M dwarfs, which are the most common type of star in our galaxy. Red dwarfs are smaller and much cooler than our Sun, which means their habitable zones are located much closer to the star. Planets orbiting within these close inhabitable zones are highly susceptible to tidal locking. Imagine such a world. One side would perpetually face its star, bathed in eternal daylight, scorching hot. The opposite side would be plunged into perpetual night, frozen and dark. This creates a dramatic quote 18 scenario, or a quote 19 world, where the only potentially temperate region would be a narrow band between the perpetual day and night sides. Could life exist on such a world? It's a question that ignites the imagination of scientists and dreamers alike. Strong winds would likely rage across the surface, attempting to equalize the extreme temperature differences, perhaps creating a band of twilight with tolerable conditions. Atmospheric circulation would play a crucial role, potentially distributing heat from the day side to the night side, or perhaps trapping it, leading to extreme conditions. Liquid water, if present, might exist in a vast ocean on the quote 20 line, or possibly even on the night side if a thick enough atmosphere could transport sufficient heat. The moon's unwavering face, a consequence of tidal locking, thus offers us a profound lens through which to contemplate the vast possibilities and challenges of life elsewhere in the universe. It reminds us that the universe is a place of incredible diversity, where the same fundamental laws can lead to wildly different outcomes. The same gravitational forces that shaped our moon into its familiar constant companion might also be creating worlds unlike anything we can fully imagine, worlds where the sun never sets on one side and never rises on the other. Our moon, therefore, is more than just a beautiful orb in the night sky. It is a cosmic teacher, a silent guardian that reveals the intricate workings of gravity, not just in our immediate vicinity, but across the entire universe. Its unchanging face is a testament to the persistent, patient work of a fundamental force, a force that choreographs the dance of planets and moons, and perhaps even shapes the very conditions for life on distant, alien worlds. As we continue to gaze upon its familiar visage, we are reminded of the elegant, interconnected nature of the cosmos and our own humble yet privileged place within its grand design. The mystery of the moon's single face, once a puzzling riddle, now unlocks a deeper, quieter sense of the universe's intricate design, inviting us to look further, to wonder more, and to learn endlessly from its timeless lessons. We have journeyed together through the cosmic ballet, unraveling the elegant mechanics that keep our moon forever facing us with its familiar visage. We've peered into the distant past, witnessing the slow, relentless waltz of tidal forces, and gazed into the far reaches of the universe, where other worlds dance their own synchronized steps. But the story of our moon, our loyal companion, is far from over. Its synchronous rotation, this seemingly simple alignment, is not merely a curious celestial quirk. It is an active, ongoing force, an unseen architect continually shaping our very home, Earth. Think of it. The moon, that silent guardian, continues its work even now. Remember how its gravitational embrace once slowed its own spin? That same invisible hand, stretched across 238,900 miles of cosmic void, still tugs at Earth, subtly but persistently. We feel its daily influence in the rhythmic ebb and flow of our oceans, the tides, those colossal waves that reshape coastlines and stir the very depths of our seas. But these are just the most visible manifestations of a far deeper, more profound interaction. For centuries, ancient mariners and coastal dwellers understood the moon's command over the waters, yet they could not grasp the full scope of its power. We now know that the moon's gravitational pull creates a bulge of water on the side of Earth facing it, and another bulge on the opposite side, where Earth itself is pulled away from the water. As our planet spins beneath these bulges, we experience the cycle of high and low tides. But this constant tugging does more than just move water. it flexes the solid Earth itself, albeit imperceptibly, creating, quote, 21, quote, that subtly deform the land beneath our feet. It is this relentless, gentle flexing, this ongoing tidal friction that continues to exert a braking effect on Earth's rotation. Just as Earth's gravity slowed the moon's gravity is slowing us. Our days, imperceptibly yet undeniably, are growing longer. We aren't talking about a sudden dramatic shift, of course. This is a change measured in milliseconds per century, a cosmic slowness almost beyond human perception. Over billions of years, however, this effect has been considerable. Geologic evidence, such as the growth patterns of ancient corals, confirms that Earth's day was once much shorter, perhaps as little as 10 hours long in its youth. Imagine a day passing in the blink of an eye compared to our current 24 hours. This process continues, driven by the very same tidal forces that locked the moon into its synchronous dance. And what of the moon itself? Its journey, too, is far from static. While tidally locked, its orbit is not perfectly circular, nor is it absolutely fixed. The same tidal interaction that slows Earth's spin also transfers angular momentum from Earth to the moon. Think of it like a slow, patient push. With each passing year, the moon steals a tiny bit of Earth's rotational energy, using it to boost itself into a slightly higher orbit. It is, in essence, slowly drifting away from us, inch by precious inch. We measure this recession with incredible precision, using laser retroreflectors left on the lunar surface by Apollo missions. We bounce lasers off these mirrors and time their return, revealing that our moon is receding by about 1.5 inches, 3.8 centimeters per year. A mere 1.5 inches may seem insignificant, a cosmic whisper in the vastness of space and time. But over billions of years, this gentle push has moved our moon from a much closer, larger appearing presence in our ancient skies to its current stately distance. What does this mean for the future? As the moon recedes, its gravitational influence on Earth will gradually diminish. The tides will become less pronounced, and Earth's rotation will continue to slow, albeit at an ever-decreasing rate. Eventually, in the unimaginably distant future, Earth's rotation could synchronize with the moon's orbital period, leading to a state of mutual tidal locking. Imagine Earth forever presenting one face to its moon, and the moon still presenting one face to Earth. It's a distant, almost poetic vision, a testament to the enduring power of gravity and the endless dance of celestial mechanics. But let us bring our focus back to the present, to a more immediate and profound consequence of our moon's presence and its tidally locked state, its role as the quiet, steadfast guardian of Earth's stability. Have you ever considered what makes Earth's climate so remarkably stable, so conducive to the flourishing of life over billions of years? Part of the answer lies with our moon and its powerful gravitational tether. Earth, like a spinning top, has an axial tilt. Our planet's axis is currently tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt is the magical ingredient that gives us our seasons, creating the beautiful variations from spring to summer, autumn to winter, that shape ecosystems and human cultures alike. Without this tilt, the sun's rays would hit the equator directly all year round, leading to extreme temperature differences between the equator and the poles, and a far less dynamic climate. However, this axial tilt is not inherently stable. Other gravitational influences in our solar system, particularly from the Sun and the gas giant planets like Jupiter, constantly tug at Earth, trying to wobble its axis to make it precess and nutate. Without a large, close moon to provide a stabilizing counter-force, Earth's axial tilt would likely swing wildly over geological timescales. Imagine the consequences. An axis that might tilt dramatically, perhaps even flipping completely upside down, leading to catastrophic climate shifts. Summers that could melt polar ice caps entirely, followed by winters that plunge tropical regions into deep freezes. Such extreme oscillations would make the sustained evolution of complex life incredibly challenging, if not impossible. Our moon, precisely because it is so massive and so relatively close, acts as a cosmic gyroscope, a gravitational anchor. Its pull provides the necessary torque to resist these external perturbations, keeping Earth's axial tilt within a relatively narrow life-sustaining range. It's an elegant, almost miraculous partnership. The very same forces that tidally locked our moon now work to stabilize our planet, ensuring that the seasons remain predictable enough for life to adapt, thrive, and evolve over eons. This is the profound, often overlooked gift of our unique moon. It is not just a light in the night sky, but an unseen architect of our planet's environmental constancy. This deeper understanding of tidal locking and its far-reaching consequences doesn't just expand our knowledge of celestial mechanics, it also profoundly informs our continued exploration of the moon itself. The far side, that mysterious hemisphere revealed to us only in 1959, becomes an even more compelling destination when we consider its unique characteristics shaped by tidal forces and crustal asymmetry. Remember the far side's thicker crust and its relative lack of Maria? This geological dichotomy, a direct result of its formation under Earth's gravitational influence, makes it a pristine canvas for scientific inquiry. Imagine, beneath that ancient crater-pocked surface lie clues to the moon's earliest history, perhaps even insights into the primordial conditions of our solar system. Scientists are already planning missions to establish radio observatories on the far side. Why there? Because the moon itself acts as a shield, blocking out the cacophony of radio signals from Earth, our cell phones, our televisions, our internet. The far side offers a radio quiet zone, unlike anywhere else in the inner solar system, an unparalleled listening post from which to detect faint signals from the universe's infancy, whispers from the very first stars and galaxies. It is a silent sanctuary, a cosmic ear, made possible by the very fact that it forever turns its back on our noisy home. And what about the near side, the face we know so well? Its vast Maria, those dark plains, tell a story of ancient volcanic activity influenced by a thinner crust and perhaps even differential tidal stresses from Earth. Future missions to the near side might focus on studying these geological features in greater detail, searching for water ice in permanently shadowed craters at the poles, or establishing bases that leverage the readily available sunlight for power. Our understanding of tidal locking, of the Earth-Moon gravitational dance, guides where we look, what questions we ask, and how we plan to live and work on our closest celestial neighbour. The exploration of the moon is not just about planting flags or collecting rocks. It is about understanding our place in the cosmos. Every mission, every rover, every laser pulse reflected back to Earth deepens our comprehension of the intricate forces that bind and shape worlds. The moon, our cosmic teacher, continues to reveal fundamental truths about gravity, geology, and the delicate balance required for life. As we gaze up at the moon, whether it's a slender crescent or a luminous full orb, we are not just looking at a rock in space. We are seeing billions of years of gravitational interaction, a testament to the persistent shaping power of tidal forces. We are witnessing the silent, elegant ballet of two celestial bodies locked in an eternal embrace, one always showing its familiar face to the other. This phenomenon, synchronous rotation, once a mystery, now stands as a profound illustration of the universe's elegant design. It is a reminder that even the most seemingly simple observations can unlock deep scientific principles. It encourages us to look closer, to question, to seek the hidden mechanics behind the visible world. So the next time you cast your eyes skyward, let a deep, quiet sense of the universe's intricate design wash over you. Remember the moon's unwavering face, the product of eons of gravitational dialogue. Remember its role as the unseen architect of our stable climate, the silent guardian of our seasons, and remember that this constant companion, this familiar friend, continues to teach us, revealing new wonders with every passing year, every new discovery. The moon is not just a mirror reflecting the sun's light. It is a profound testament to the interconnectedness of all things, a cosmic riddle whose solution continues to inspire awe and ignite our boundless curiosity. The journey of understanding, much like the moon's own journey, is eternal, always revealing new horizons, new questions, new depths of wonder. And we, as curious explorers, are privileged to be a part of it. We've seen how our moon, in its silent orbit, acts as a cosmic teacher, revealing fundamental truths about gravity, geology, and the delicate balance required for life. But its lessons are far from over. Indeed, one of its most profound classrooms lies on that enigmatic far side, forever turned away from our terrestrial gaze, a sanctuary of silence, a canvas for the universe's earliest whispers. Think about it. Our Earth, vibrant with life and teeming with technology, is a broadcasting station of immense power. Every radio signal, every cell phone conversation, every television broadcast, every Wi-Fi router, every radar ping, they all contribute to a pervasive blanket of electromagnetic noise. This terrestrial din, while a testament to our ingenuity, is a deafening roar to astronomers trying to listen for the faint, ancient murmurs from the cosmos. It's like trying to hear a whispered secret across a stadium during a rock concert. This is where the moon's far side becomes an unparalleled treasure. Shielded by 2,159 miles, 3,474 kilometers of solid lunar rock, this hemisphere offers an almost perfect radio quiet zone. Imagine, if you will, a place utterly untouched by the cacophony of human existence, a pristine observatory where the universe can speak to us without interruption. This isn't just a quiet spot. It's the quietest place we know of in the inner solar system, a natural shield against the relentless chatter of our home planet. What cosmic secrets are we hoping to uncover from this lunar sanctuary? The primary target is the faint radio emission from the very early universe, specifically from the period known as the Hassas, 25, and the subsequent (26.6). These are not just fancy astronomical terms, they represent pivotal chapters in the universe's autobiography. The cosmic dark ages began about 380,000 years after the Big Bang. once the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this, the universe was a hot, dense plasma, opaque to light. But once neutral atoms formed, light could travel freely, giving us the cosmic microwave background, CMB, the universe's oldest light, a snapshot of its infancy. However, after the CMB, the universe entered a period of profound darkness. There were no stars, no galaxies, just a vast expanse of neutral hydrogen, slowly cooling and expanding. This period lasted for hundreds of millions of years, a cosmic lull before the storm of star formation. Then came the epoch of rionization. Sometime between 150 million and a billion years after the Big Bang, the very first stars and galaxies ignited. These colossal stellar engines emitted intense ultraviolet radiation, slowly but surely stripping electrons from the neutral hydrogen atoms, reionizing the universe. This transformation from a dark, neutral cosmos to a bright, ionized one is a fundamental event that shaped everything we see today. The key to studying these epochs lies in observing the faint radio signals emitted by that neutral hydrogen. This specific signal, known as the 21 centimeter line, or hydrogen line, is a unique spectral signature. It's incredibly weak, redshifted to even longer wavelengths by the universe's expansion, and easily drowned out by terrestrial interference. From Earth, or even from Earth orbit, our own radio noise obscures these ancient whispers. But from the far side of the Moon, we gain an unprecedented advantage, an unblemished window into these formative years. What would we learn? We could map the distribution of matter in the early universe, track the growth of the first structures, and understand the processes that led to the formation of the first stars and galaxies. We could trace the cosmic web as it began to form, revealing the scaffolding upon which all subsequent cosmic evolution unfolded. It's like finding a lost diary detailing the childhood of the universe itself, offering insights into its origins that are simply unobtainable anywhere else. Of course, nothing truly grand comes without its trials. Building and operating a radio observatory on the far side of the Moon presents a formidable array of challenges. The lunar environment itself is a formidable adversary. Extreme temperatures swing wildly between scorching day and frigid night, ranging from around 250 degrees Fahrenheit, 120 degrees Celsius, to minus 280 degrees Fahrenheit, minus 173 degrees Celsius. The lunar dust, often described as regolith, is abrasive, electrostatically charged, and gets everywhere, posing a threat to sensitive equipment and machinery. And then there's the radiation. Without a thick atmosphere or a global magnetic field like Earth's, the lunar surface is exposed to a constant barrage of cosmic rays and solar radiation, necessitating robust shielding for both instruments and human explorers. Logistically, the far side is even more demanding. Communication with Earth is a significant hurdle. Since the Moon always presents the same face to us, a direct line of sight from the far side to Earth is impossible. This means any far side observatory would require a relay satellite network, perhaps orbiting the Moon, to transmit data and receive commands. Imagine the precision engineering and orbital mechanics required to maintain such a continuous communication link. Power generation, too, is a critical concern, especially during the 2-week-long lunar night. Solar panels would need to be supplemented by advanced battery storage or even compact nuclear power sources to keep instruments operational. But these challenges are not deterrents, they are invitations. They push the boundaries of our engineering capabilities, inspiring innovation and fostering a new generation of space technologies. Overcoming these hurdles isn't just about building a telescope. It's about developing the infrastructure and expertise for long-term lunar habitation and resource utilization. The Moon isn't merely a destination for telescopes, it's a proving ground, a cosmic stepping stone. Consider the broader implications. Establishing a permanent human presence on the Moon, perhaps initially to support scientific endeavours like the Far Side Observatory, opens up a new frontier for humanity. It allows us to test life support systems, develop techniques for extracting water ice from shadowed craters for propellant and drinking water, and learn to live and work in an extraterrestrial environment. These are not just theoretical exercises, they are crucial preparations for even more ambitious journeys to Mars, to the asteroid belt, and eventually beyond. The Moon, our constant companion, becomes our first extraterrestrial classroom for living off-world. And so, our cosmic teacher continues to guide us, not just through the elegant mechanics of its orbit and the profound stability it imparts to Earth, but also through the silent promise of its hidden side. The far side of the Moon, once a blank canvas of mystery, is now envisioned as a pristine laboratory, a portal to the universe's origins, and a testament to humanity's unyielding quest for knowledge. It reminds us that the universe is an endless source of wonder, a tapestry woven with forces and phenomena far grander than our everyday experience. Each question we answer about the Moon, about gravity, about the delicate dance of celestial bodies, simply births a constellation of new ones. And in that continuous cycle of inquiry and discovery, we not only learn about the cosmos, but we learn more about ourselves, our boundless curiosity, our relentless drive to explore, and our profound connection to the vast, silent, and endlessly fascinating universe we inhabit. The Moon, in its steadfast vigil, beckons us to look deeper, to listen closer, and to dream bigger. Our journey into the Moon's enigmatic embrace brings us back, full circle, to its unseen face, a canvas of mystery, a sanctuary of silence, and a proving ground for humanity's grandest ambitions. We've unravelled the cosmic ballet that keeps one side forever turned toward us, a gravitational lock forged over eons. But what secrets does that hidden hemisphere truly hold, beyond its stark, crater-pocked terrain? And what does its silent vigil mean for our future among the stars? Imagine, if you will, a place on Earth so utterly devoid of human chatter, so pristine in its quietude, that you could hear the faint echoes of creation itself. Such a place does not exist on our bustling blue planet. But on the Moon's far side, shielded by its very bulk from Earth's cacophony of radio signals, our television broadcasts, our mobile phone chatter, our military radar, our countless electronic whispers, we find that ethereal silence. This isn't just an absence of noise, it is a profound cosmic quiet, a vacuum of interference that offers an unparalleled window into the universe's earliest moments. We are talking about more than just a quiet spot for a telescope. We are envisioning an observatory unlike any other, precisely because of the Moon's synchronous rotation. That constant, unchanging shield means that any radio antenna placed on its far side would forever be protected from Earth's radio pollution. It's a natural Faraday cage, a silent sentinel poised to listen to the universe's most ancient whispers. What whispers, you ask? We are seeking the faint, elusive radio signals from the cosmic dark ages, a period stretching from about 370,000 years after the Big Bang, when the universe cooled enough for neutral hydrogen atoms to form, to roughly 1 billion years later, when the first stars and galaxies ignited. Before this epoch of reionization, the universe was a vast, dark expanse, filled with this neutral hydrogen, a cosmic fog obscuring everything. There were no stars, no galaxies, only the remnants of the Big Bang cooling and expanding. This primordial hydrogen, though invisible to our optical telescopes, emits a faint radio signal at a specific wavelength, the 21 centimeter line. Detecting this signal today, stretched by the universe's expansion into much longer wavelengths, is an astronomical holy grail. It would allow us to map the distribution of matter in the early universe, to understand how the first structures began to coalesce, and to witness the very first flickers of light as the universe transitioned from darkness to dawn. It's like trying to hear the first breath of a newborn universe, a sound swallowed by billions of years and cosmic expansion. On Earth, this signal is utterly swamped by our own technological noise, but on the Moon's far side, we have a chance. Consider the immense implications. By charting these nascent structures, we can refine our models of cosmology, testing the very fabric of our understanding of the Big Bang, dark matter and dark energy. We could glimpse the universe before galaxies formed, before black holes grew, before the cosmic web began to weave its intricate tapestry. It is a journey back in time, not just in theory, but in direct observation, made possible by the Moon's steadfast rotation and its silent, protective bulk. But the promise of the far side extends beyond this cosmic archaeology. It's also a proving ground, a crucible for humanity's next great leap into the cosmos. Building and maintaining an observatory, or indeed any permanent human presence, on the far side of the Moon presents a formidable array of challenges. We've touched upon some of them. The extreme temperature swings from searing day to freezing night, the abrasive lunar regolith that clings to everything and wears down machinery, the constant barrage of solar and cosmic radiation unimpeded by an atmosphere, and the monumental task of communication without a direct line of sight to Earth. Yet, these challenges are not deterrents. They are invitations. They are the rigorous tests that will forge the technologies, strategies, and human resilience necessary for sustained deep space exploration. How do we construct habitats that protect against radiation and micrometeorites? We might use lunar regolith itself, melting it into bricks or 3D printing structures directly on the surface, leveraging the very environment as a resource. How do we generate power through the long lunar night? Advanced solar arrays paired with robust energy storage systems, or perhaps even compact nuclear fission reactors, become essential. How do we ensure reliable communication? A network of relay satellites in lunar orbit, perpetually linking the far side to Earth, becomes our indispensable cosmic switchboard. These are not mere engineering problems. They are catalysts for innovation that will ripple through every aspect of our lives, much like the space race of the 20th century, spurred advancements in computing, materials, science, and medical technology. The solutions we devise for lunar living, closed-loop life support systems that recycle air and water, advanced robotics for construction and maintenance, efficient resource extraction from lunar ice, will be directly applicable to future missions to Mars, to asteroid mining, and eventually to human settlements beyond our home planet. The moon, in its silent, elegant way, becomes our cosmic classroom, teaching us how to survive, thrive, and expand our reach across the solar system. Think of the psychological and physiological adaptations required for humans to live for extended periods in a low-gravity, high-radiation environment, far from the familiar sights and sounds of Earth. What will it mean for our bodies, our minds, our social structures? The moon will be where we learn these lessons, where we understand the true meaning of becoming an interplanetary species. It is a giant leap, yes, but it begins with a series of measured, deliberate steps on our nearest celestial neighbour. The quote 30 that the moon presents to us, a direct consequence of tidal locking, becomes more than just an astronomical curiosity. It is a symbol, a constant reminder of the universe's intricate mechanics and our place within them. For millennia, its familiarity has grounded us, inspired poets, and guided navigators. Now, as we understand the forces that shaped its rotation, we are poised to use that very understanding to push the boundaries of our knowledge. The moon, our constant companion, has patiently waited. It has played its role as Earth's, quote 30, stabilizing our planet and making life possible. Now it stands ready to serve as our launch pad, our training ground, our silent partner in the grand adventure of cosmic discovery. This journey to the moon's far side is not merely about science or technology. It is about the indomitable human spirit of exploration. It is about our innate drive to understand, to push beyond the known, to answer the whispered questions of the universe. The moon, with its steadfast one-sided gaze, challenges us not just to observe, but to participate. It invites us to build, to innovate, to adapt, and to listen. From the quiet elegance of its synchronous rotation, we glean a deeper appreciation for the universe's persistent forces, the invisible hand of gravity shaping worlds and destinies. We realize that the moon, our familiar friend, is a profound teacher, revealing not only the mechanics of the cosmos, but also the boundless potential within ourselves. As we gaze upon it, whether through a telescope or with the naked eye, we are reminded that every mystery solved opens the door to countless new wonders, beckoning us further into the vast luminous tapestry of existence. The moon, our silent guardian, continues to illuminate our path forward, guiding humanity's quest for knowledge and our inevitable destiny among the stars. Our journey through the moon's silent ballet, its intricate dance of rotation and revolution, has unveiled so much. We've explored the gravitational embrace that shaped its destiny, the cosmic forces that slowed its spin to a perfect synchronicity, and the profound impact it has on our very existence. We've peered into the hidden hemisphere, once a mystery, now a canvas of ancient impacts and unique geological tales. But what does this knowledge truly mean for us, for humanity, as we gaze upon our constant companion? Where do we go from here, as the moon continues to beckon, whispering secrets that stretch from the dawn of time to the farthest reaches of the universe? The moon, our cosmic teacher, has laid before us a profound invitation. It challenges us not just to understand why we only see one side, but to actively explore what lies beyond that familiar face, and how those hidden depths can illuminate our path among the stars. The next chapter in our lunar saga isn't just about passive observation. It's about active engagement, about reaching out and touching the very fabric of cosmic history. Consider the far side, that enigmatic hemisphere we've discussed, shielded from Earth's clamour. We've learned that its geological differences, its thicker crust, its scarcity of Maria, tell a unique story of early lunar evolution, a tale distinct from the near side's volcanic plains. But its true allure, the reason it draws our gaze with such magnetic force today, extends far beyond its ancient geology. The far side is, quite simply, the quietest place we know in the inner solar system. It is a sanctuary, a pristine canvas for an entirely new kind of astronomy. Imagine, if you will, the cacophony of Earth. Every cell phone call, every radio broadcast, every television signal, every Wi-Fi router, every spark of human technology creates a symphony of electromagnetic noise. This static, this constant chatter, washes over our planet and extends into space, blinding our terrestrial instruments to the faintest whispers from the cosmos. It's like trying to discern a delicate melody in the heart of a bustling modern city. But on the moon's far side, you see, it is different. The entire bulk of our celestial partner acts as a magnificent natural shield, blocking out Earth's radio interference. It is a zone of profound, almost sacred radio silence. This isn't merely a convenience. It is a gateway to understanding the earliest moments of our universe. We are talking about the cosmic dark ages, that epoch following the Big Bang, when the universe was filled with neutral hydrogen, before the first stars and galaxies ignited, and then the epoch of rionization, when those nascent celestial bodies began to flood the cosmos with ultraviolet light, stripping electrons from that neutral hydrogen and fundamentally transforming the universe. These periods are invisible to optical telescopes, but they left a faint, telltale signature in the form of incredibly long wavelength radio waves. These are the whispers we seek, the primordial echoes of creation itself, stretched and dimmed by billions of years of cosmic expansion. To detect these faint signals, we need immense radio telescopes, not like the dish antennas we might picture, but vast arrays of simple dipole antennas spread across kilometers of lunar regolith. These instruments, designed to listen to frequencies that Earth's atmosphere usually blocks, or Earth's technology drowns out, would be able to capture the ghostly imprint of the very first atoms forming, the first structures emerging from the cosmic void. What profound insights could we glean from hearing the universe's infancy? What fundamental truths about matter, energy, and the very structure of reality might be unveiled? The far side of the moon promises to be our ear to the beginning of everything. But the scientific bounty of the far side isn't limited to radio astronomy. Its unique environment offers a multitude of other unparalleled research opportunities. Consider, for instance, the continuous stream of solar wind particles, unfiltered by Earth's protective magnetosphere. On the far side, we could study these particles directly, understanding their composition, energy, and how they interact with planetary surfaces, providing crucial data for understanding space weather and planetary evolution across our solar system. Then there's the moon's interior. We've hinted at the geological asymmetry between the near and far sides, but a network of advanced seismometers placed across the far side could finally map the moon's internal structure with unprecedented detail, revealing the secrets of its core, mantle, and crust. and shedding light on its formation and evolution. Imagine building a detailed 3D model of our moon, layer by elegant layer, a blueprint of its billions of years of existence. Of course, pursuing these grand scientific ambitions is no small feat. The moon, particularly its far side, is a land of extremes. We speak of the abrasive regolith, a dust so fine and sharp it can infiltrate everything. The relentless bombardment of cosmic radiation, unchecked by an atmosphere. The dramatic temperature swings between scorching lunar day and frigid lunar night, often plunging hundreds of degrees below zero. And the immense challenge of communication as the Earth-facing side blocks direct line of sight. These are not mere inconveniences, they are formidable adversaries. Yet, it is precisely these challenges that become our greatest teachers, our most potent drivers of innovation. How do we design habitats that protect against radiation and micrometeorites? How do we develop robotics that can withstand the abrasive dust and extreme thermal cycles? How do we establish reliable communication networks, perhaps using a constellation of relay satellites in lunar orbit, to bridge the divide between Earth and the far side? How do we harness local resources, like the water ice believed to exist in permanently shadowed craters at the lunar poles, to sustain human presence, to create breathable air, to produce rocket fuel? This concept of, quote, 35, quote, or ISRU, is not just a clever idea, it is the cornerstone of sustainable deep space exploration. The moon, with its potential reserves of water, oxygen, and even helium-3, a potential fuel for future fusion reactors, becomes more than just a scientific outpost. It transforms into a potential wellspring for humanity's expansion. Imagine processing lunar regolith to extract metals for construction, or using lunar ice to refuel missions bound for Mars and beyond. The moon becomes a cosmic gas station, a shipyard, a training ground, a place where we learn to live and thrive beyond the cradle of Earth. And this truly is where the moon's role as a, quote, 36, quote, reaches its zenith. Establishing a sustained human presence on the far side, facing its unique environmental and logistical hurdles, serves as an invaluable proving ground for our ultimate aspirations, sending humans to Mars and eventually perhaps even further into the solar system. The moon is closer, more forgiving, relatively speaking, and offers a chance to test every technology, every procedure, every physiological and psychological challenge that long-duration space travel presents. How do humans adapt to prolonged low gravity? How do we manage radiation exposure over months or years? How do we build self-sufficient life support systems? The answers, we believe, lie on the moon. We are not just talking about quick flag and footprint missions anymore. We envision permanent lunar bases, research stations, perhaps even small settlements. These outposts would not only facilitate groundbreaking scientific discovery, but would also foster a new space economy, driving technological advancements that ripple back to Earth, benefiting us all. The moon, once a distant, enigmatic orb, slowly transforms into an extension of our reach, a tangible step in humanity's journey to become a multiplanetary species. The far side, once a symbol of the unknown, of what lay hidden and inaccessible, now represents a beacon for our future. Its silence is not emptiness, but a profound invitation to listen. Its rugged terrain is not an obstacle, but a challenge to innovate. Its distance is not a barrier, but a measure of our ambition. As we look up at the moon tonight, We are not merely observing a celestial body. We are looking at a mirror reflecting our own curiosity, our own ingenuity, our own relentless drive to explore. The moon, with its unwavering, unchanging face, has, through the elegant mechanics of tidal locking, presented us with a gift. A shielded sanctuary, a cosmic observatory, a training ground for the stars. It is a reminder that the universe, in its intricate design, holds endless wonders, and that our journey of discovery, fueled by curiosity and courage, is truly just beginning. The moon's silent presence continues to inspire us, urging us to step beyond the familiar, to embrace the unknown, and to reach for the boundless horizons that await. Our constant companion, the moon, continues to teach us about the cosmos and our potential within it. But what does this truly mean? This idea of the moon as a proving ground. It means that our understanding of its steadfast face, its ancient geology, and its unique far side is not merely an academic pursuit. It is the very foundation upon which we are building humanity's next giant leap. We are not just gazing at the moon, we are learning from it, preparing ourselves for journeys far beyond its familiar orbit. Think of it this way. If Earth is our cradle, then the moon is our cosmic playground, a challenging yet accessible training ground. Here, just a 3-day journey away, we can test the limits of our technology, the resilience of the human spirit, and the ingenuity of our engineering. Why the moon, you might ask, when Mars beckons with its own rusty allure? Because the moon presents a crucial intermediate step, a Goldilocks zone of challenge, not so easy as Earth, but not as brutally distant and demanding as the red planet. Its low gravity, lack of a protective atmosphere, extreme temperature swings, and pervasive radiation offer a distilled version of the challenges we will face on Mars, allowing us to refine our tools and strategies before committing to a mission that could take years, not days. One of the most critical lessons we are learning, and indeed one of the cornerstones of future deep space exploration, revolves around in situ resource utilization, ISRU. Imagine a pioneer setting out across a vast empty continent, not carrying every single supply from their starting point, but instead learning to live off the land. This is precisely what ISRU means for space exploration. Every pound of water, every breath of oxygen, every structural beam we launch from Earth costs thousands of dollars. It's an unsustainable model for long-duration missions. But what if we could quote 38 on the moon? We know, thanks to decades of robotic missions and careful analysis, that the moon holds vast reserves of water ice, particularly in the permanently shadowed craters at its poles. This isn't just a scientific curiosity, it's a game changer. Water, that miraculous molecule, can be melted for drinking, purified for hygiene, and most importantly broken down through electrolysis into hydrogen and oxygen. Hydrogen and oxygen are the very components of rocket fuel. Imagine being able to refuel our spacecraft at a lunar gas station, using resources harvested directly from the moon itself. This transforms the moon from a mere destination into a cosmic filling station, a vital waypoint for journeys to Mars and beyond. We could launch missions to the red planet already fueled, shedding the immense mass of fuel tanks from their Earth-based launch, making these ambitious voyages far more feasible and economical. Beyond fuel, lunar water ice can contribute to breathable air and radiation shielding. But what about building structures? The moon's surface is covered in a fine, abrasive dust called regolith, a material that has plagued every lunar mission to date, clinging to everything. Yet this very regolith, once seen as a nuisance, is now viewed as a valuable construction material. Scientists and engineers are developing techniques to melt and sinter regolith, essentially 3D printing habitats, landing pads, and radiation shelters directly on the lunar surface. Picture robotic builders, guided by our commands, laying down layer after layer of lunar soil, creating durable structures that protect astronauts from the harsh vacuum, extreme temperatures, and ever-present radiation. This isn't science fiction. It's the future we are actively building, piece by intricate piece, right now. Speaking of radiation, it is one of the most formidable adversaries in deep space. Earth's magnetic field and thick atmosphere act as an invisible shield, deflecting harmful cosmic rays and solar particles. The moon, however, offers no such protection. Astronauts on the lunar surface are exposed to significantly higher levels of radiation, posing serious health risks. Learning to mitigate this exposure is paramount for any long-duration human presence beyond Earth. Here too, the moon serves as our laboratory. We are exploring various shielding strategies, from burying habitats under layers of regolith, a natural abundant shield, to developing advanced materials and even considering active magnetic shielding technologies that could create miniature, artificial magnetospheres around habitats or spacecraft. These innovations, honed on the moon, will be directly transferable to Mars missions, where the radiation environment, though slightly less severe than on the moon due to a thin atmosphere, still demands robust protection. And then there are the challenges of sustaining human life in a truly alien environment. On Earth, our complex biosphere continuously recycles air, water, and waste. In space, every resource is finite. This pushes us to develop closed-loop life support systems that can recycle nearly 100% of air and water, and even process waste for potential reuse. Imagine a miniature, self-sustaining ecosystem within a habitat where every drop of water is reclaimed, every breath of air is scrubbed and reoxygenated. These are the systems we are testing on the moon, the critical infrastructure that will allow humans to live and work independently for extended periods, far from Earth's nurturing embrace. The vastness of space also demands a new breed of worker, robots and autonomous systems. While human ingenuity and adaptability remain irreplaceable, the sheer scale of building and maintaining a lunar outpost, especially on the far side, necessitates sophisticated robotic assistance. These metallic pioneers can perform dangerous tasks, work tirelessly in extreme conditions, and conduct preliminary surveys and construction before humans even arrive. Imagine robotic excavators digging for water ice, autonomous rovers mapping complex terrain, and intelligent drones inspecting critical infrastructure. For the far side's radio observatory, these robots become the primary builders and maintainers, working in an environment where direct human intervention might be limited due to the challenges of communication and logistics. Their development and deployment on the moon will refine the algorithms and hardware needed for similar operations on Mars, where communication delays make direct, real-time control from Earth impossible. Communication itself presents a unique challenge, particularly when dealing with the moon's far side. As we discussed, that silent hemisphere is perpetually turned away from Earth, necessitating relay satellites to maintain contact. This introduces communication delays and complexities that, while not as extreme as those experienced with Mars, which can range from 3 to 22 minutes one way, provide invaluable experience. We learn to manage data flow, handle latency, and develop protocols for asynchronous operations. These are crucial skills for Mars missions, where a simple hello can take many minutes to arrive, and a command sent from Earth might not be executed until long after it was transmitted. And what of the human element? The psychological toll of isolation, confinement, and living in an extreme high-stakes environment cannot be underestimated. Long-duration missions to the Moon will serve as invaluable opportunities to study human resilience, team dynamics, and the effectiveness of countermeasures against stress and fatigue. How do we best support astronauts far from home? What routines, technologies, and psychological strategies are most effective? The Moon offers a relatively safe space to gather this crucial data, preparing us for the even greater psychological demands of a multi-year journey to Mars. It is against this backdrop of scientific discovery and technological innovation that programs like Artemis are taking shape. Artemis is not just about returning humans to the Moon. It is about establishing a sustainable human presence there, building a base, and ultimately using the Moon as a stepping stone, a launch pad for our journey to Mars. Central to this vision is the Lunar Gateway, an orbital outpost that will orbit the Moon, serving as a staging point for lunar surface missions, a science laboratory, and a vital communication relay. From the gateway, astronauts can descend to the lunar surface in specialized landers, conduct their work, and then return to the orbiting station, ready for their next mission or their journey back to Earth. This infrastructure, this orbital hub, is directly analogous to the kind of staging posts we might one day build around Mars or other celestial bodies. And the far side, that once mysterious unseen hemisphere, plays a truly unique role in this grand future. Its radio-quiet zone, shielded from Earth's incessant chatter, remains an unparalleled location for unlocking the universe's deepest secrets. Imagine vast arrays of radio telescopes, built by autonomous robots and powered by lunar resources, listening for the faint whispers of the cosmic dark ages. The era before the first stars ignited, when the universe was a vast dark expanse of neutral hydrogen. This is the ultimate astronomical frontier, a window into the universe's infancy, and the Moon's far side offers the only truly quiet vantage point from which to peer through it. Establishing such an observatory requires mastering everything we've discussed. Yizru for construction, robotics for deployment, advanced communication relays, and radiation protection for any human maintenance crews. So, you see, the question, why do we only see one side of the Moon, unravels into a tapestry of profound scientific understanding, technological ingenuity, and a bold vision for humanity's future. The synchronous rotation, the tidal forces, the geological asymmetry, these aren't just fascinating facts. They are pieces of a cosmic puzzle that, once assembled, reveal the Moon not as a static, unchanging orb, but as a dynamic teacher, a silent guide, and an indispensable proving ground. The Moon, our familiar friend, is beckoning us to understand its hidden depths, both literally and figuratively, so that we may, in time, reach for the stars. It is a testament to the intricate design of the universe and to our own relentless curiosity that the answer to a seemingly simple question can unlock such boundless potential. The journey continues, and the moon remains our steadfast companion, illuminating the path forward. We stand at a precipice, gazing not just at the familiar face of our lunar companion, but into its very future, and, through it, our own. The moon, our constant companion, our silent guardian, now beckons us with promises of unprecedented scientific discovery and a proving ground for humanity's grandest cosmic ambitions. We've unravelled the elegant dance of its synchronous rotation, understood the deep scars on its far side, and recognised its profound influence on our home planet. Now, we turn our gaze to what comes next, to the endeavours that will transform our understanding of the universe and our place within it. Think of the far side, that shielded hemisphere, not merely as a barren expanse but as a pristine cosmic canvas, untouched by the cacophony of Earth's radio chatter. It is the ultimate radio quiet zone, a sanctuary of silence that offers us an unparalleled window into the universe's earliest moments. Imagine, if you will, standing in a crowded, noisy room, trying to hear a whispered secret from across the globe. Impossible, right? Now imagine stepping into a soundproof chamber, vast and still, where every faint murmur from the most distant reaches of space can be heard with astonishing clarity. That, dear reader, is the promise of the lunar far side. What exactly are we listening for in this cosmic quietude? We are straining our ears for the faint ancient whispers of the universe's infancy, signals from the quote 41 and the quote 42. These aren't just poetic names. They describe critical chapters in the universe's autobiography, periods before the first stars ignited, before the first galaxies bloomed into being. We are talking about the primordial hydrogen gas, cold and neutral, that permeated the universe just a few 100,000 years after the Big Bang. This gas emits a specific wavelength of radio light, the quote 43, which due to the universe's expansion stretches into much longer wavelengths by the time it reaches us. Detecting these incredibly faint red-shifted radio waves is like reading the universe's baby pictures, offering us direct insights into how the very first structures in the cosmos began to form. It's the ultimate archaeological dig, but instead of uncovering ancient pottery, we are uncovering the very fabric of existence, tracing the lineage of every star, every galaxy, every atom back to its earliest origins. The engineering challenges of building and operating a radio observatory on the far side are immense, a testament to our ingenuity. How do you deploy vast arrays of antennas in a vacuum, under extreme temperatures, with abrasive regolith, and without direct communication with Earth? It demands a symphony of robotics and autonomous systems working in concert. Imagine robotic rovers meticulously unspooling kilometers of antenna wire, self-assembling components, and performing maintenance tasks without human intervention. Picture sophisticated AI algorithms sifting through cosmic noise, autonomously identifying and amplifying those faint 21-centimetre signals. Power generation becomes critical, perhaps vast solar arrays unfolding under the relentless lunar sun, or even small nuclear fission reactors providing a constant energy supply through the long lunar nights. And communication, that's where the Lunar Gateway, our orbital outpost, becomes a vital relay. a silent sentinel ensuring that the priceless data collected on the far side finds its way back to us, unlocking secrets woven into the very fabric of space-time. This isn't just about building a telescope. It's about building a scientific outpost that pushes the boundaries of automation, resilience, and deep space operations. But the moon is more than just a cosmic listening post. It is also humanity's ultimate proving ground for deep space exploration. If we are to venture to Mars and beyond, if we are to truly become a multiplanetary species, we must first master living and working sustainably on our nearest celestial neighbour. The moon presents an array of challenges that are scaled-down versions of what we will face on Mars, yet formidable enough to demand revolutionary solutions. The extreme temperatures, swinging from scorching lunar day to frigid lunar night, the ever-present threat of radiation from solar flares and galactic cosmic rays, the abrasive, clinging lunar regolith that can degrade equipment and endanger habitats, and the communications delays that make real-time human interaction with Earth impossible. Each of these is a puzzle, and solving them on the moon provides the blueprints for our journeys across the solar system. At the heart of this proving ground concept lies in situ resource utilization, or ISCRU. This isn't just a fancy term, it's the key to turning lunar dust into gold, or more accurately, lunar ice into fuel and air. Think of it. Instead of hauling every drop of water, every breath of oxygen, and every kilogram of rocket fuel from Earth, we learn to live off the land. We know there's water ice in the permanently shadowed craters at the lunar poles. Imagine robotic drills boring into the frigid regolith, extracting this precious ice. Once melted and purified, this water becomes potable drinking water for our astronauts, life-sustaining oxygen for their habitats, and, through electrolysis, hydrogen and oxygen propellants for rockets. Picture a lunar gas station, fueled by the moon itself, ready to top off spacecraft bound for Mars. And what about shelter? The very regolith, that fine dusty soil that clings to everything, becomes our building material. We envision massive 3D printers autonomously constructing habitats, landing pads, and radiation shields using lunar soil as their feedstock. These structures, built with local materials, offer inherent protection from radiation and micrometeorites, creating a durable, sustainable infrastructure for future lunar settlements. This self-sufficiency, this ability to quote 45, quote, is not just an advantage. It is an absolute necessity for any long-duration human presence beyond Earth. The relentless assault of space radiation is another formidable adversary. On Earth, our atmosphere and magnetosphere shield us, but on the moon, astronauts are exposed. Developing robust radiation mitigation strategies is paramount. We're exploring concepts like burying habitats under several meters of lunar regolith, creating natural radiation bunkers. We're researching advanced materials for spacecraft and habitat walls, engineered to block harmful particles. We're even investigating pharmaceutical countermeasures to protect the human body at a cellular level. It's a multi-layered defense, a cosmic shield woven from ingenuity and scientific understanding. And then there are the challenges of simply living in a self-contained environment for months or even years. This is where closed-loop life support systems come into play. Imagine a miniature Earth ecosystem, meticulously engineered to recycle everything. Water is filtered and reused, air is scrubbed clean and replenished, and waste is processed and repurposed. Astronauts will grow their own food in lunar greenhouses, perhaps using hydroponics or aeroponics, further reducing reliance on Earth. This level of self-sufficiency requires unprecedented reliability and redundancy, pushing the boundaries of environmental control and biological systems. It's about creating a sustainable bubble of life in the unforgiving vacuum of space. The Moon also serves as the ultimate testbed for robotics and autonomous systems, with communication delays making real-time control from Earth impractical. Future lunar missions will rely heavily on intelligent machines. We envision fleets of robots performing dangerous tasks like prospecting for resources, constructing infrastructure, maintaining equipment, and even assisting astronauts with complex scientific experiments. These robots will need to be resilient, capable of self-repair, and able to make independent decisions within predefined parameters. They are our tireless cosmic laborers, extending our reach and capabilities far beyond what human hands alone could achieve. And to connect it all, to bridge the vast silence between Earth and the lunar far side, we are building advanced communication networks. The Lunar Gateway, orbiting the Moon, will act as a central hub, relaying data and commands between Earth and lunar surface assets, including those on the far side. Imagine a dedicated internet for the Moon, a high-speed data highway ensuring that scientists on Earth can receive real-time telemetry from their far-side observatories, and that astronauts can communicate with their families, albeit with a slight delay. This network is the nervous system of our future lunar presence, vital for both scientific discovery and human well-being. Ultimately, all these technological advancements converge on a singular, profound goal: establishing a sustainable human presence on the Moon. Programs like Artemis are not just about planting flags, they are about building a permanent foothold, a lunar village, a launching pad for humanity's expansion into the solar system. The Moon, with its lower gravity and lack of atmosphere, offers a far more energy-efficient departure point for missions to Mars and beyond. It takes significantly less fuel to launch a spacecraft from the Moon than from Earth, making it an ideal staging post, a cosmic gas station and shipyard rolled into one. But beyond the technical and logistical necessities, there is the human element, the enduring spirit of exploration that drives us. What does it mean for us, as a species, to live off-world, to establish a permanent presence on another celestial body? It challenges our very definition of home. It forces us to adapt, to innovate, to collaborate on an unprecedented scale. We learn about the psychological and physiological adaptations required for long-duration space living, for coping with isolation, confinement, and the unique stresses of a harsh alien environment. The Moon becomes our classroom, teaching us how to be truly interplanetary. The Moon, our silent guardian, once a source of ancient myths and wonder, now stands as a beacon for our future. It is a cosmic riddle that, as we unravel it, reveals not just the intricate mechanics of the universe, but also the boundless potential of human curiosity and ingenuity. From listening to the faintest echoes of creation on its far side to building the foundations of a new civilization on its surface, the Moon is calling us forward. It is teaching us that the elegant ballet of celestial mechanics, the quiet dance of gravity and light, is not just a spectacle to behold, but an invitation to participate, to become active architects of our cosmic destiny. As we look up at that familiar, unchanging face, we realize that the journey of understanding why we only see one side has led us to the very edge of human endeavor, poised to take the next giant leap. The moon is not just a destination. It is a stepping stone, illuminating the path to a future where humanity's reach truly extends to the stars. We stand on the precipice of a new era, gazing at our silent guardian, the moon, not merely as a celestial object, but as the ultimate proving ground for humanity's deepest aspirations. We've unravelled the elegant dance of its synchronous rotation, celebrated its role as Earth's steadfast companion, and glimpsed the secrets held within its far side. But now the question shifts from why it is so to how we will truly make it our own. How do we not just visit but live there? How do we transform a barren rock into a crucible for interstellar ambition? This is where the dream meets the dust, where our ingenuity is tested against the unforgiving reality of a world without atmosphere, without a magnetic shield, a world of extremes. Building a sustainable human presence on the moon is an endeavour fraught with monumental challenges, each demanding revolutionary solutions that will, in turn, unlock the doors to Mars and beyond. It is here, under the pale glow of Earth, that we will forge the very tools, master the very techniques, and cultivate the very resilience needed to become a truly multi-planetary species. Think of the moon not as a distant destination, but as a cosmic boot camp, an intense training ground where every lesson learned carries the weight of our future. What are these formidable obstacles, you ask, that make establishing a lunar outpost so uniquely difficult? First, consider their extreme temperatures. Imagine a world where the sun-drenched day can scorch surfaces to over 250 degrees Fahrenheit, 121 degrees Celsius, hot enough to boil water, only to plummet to a frigid negative 208 degrees Fahrenheit, negative 133 degrees Celsius, during the 2-week-long night. This isn't just a challenge. It's a constant, brutal oscillation that demands materials, systems, and habitats capable of enduring such colossal swings without fail. Our structures must be thermal fortresses, insulating against both the searing heat and the bone-chilling cold, often harnessing the very regolith beneath our feet for passive shielding. We must engineer power systems, perhaps nuclear fission reactors or advanced solar arrays with robust energy storage that can reliably operate through prolonged darkness. Then there is the infamous abrasive lunar regolith. This isn't just dirt, it's a fine jagged powder, the product of billions of years of micrometeorite impacts pulverizing rock in a vacuum. Each grain is a microscopic shard of glass, insidious and pervasive. It clings to everything, infiltrates seals, grinds down moving parts, scratches lenses, and even poses a health risk if inhaled. For the Apollo astronauts, it was an annoyance, a gritty souvenir. For long-term inhabitants, it's a relentless enemy. How do we design dust-resistant mechanisms? How do we clean habitats and equipment? How do we protect our lungs? This seemingly mundane problem forces us to innovate new materials, electrostatic dust shields, and advanced filtration systems, lessons that will be invaluable when dealing with Martian dust storms. And what about radiation? Unlike Earth, with its protective atmosphere and magnetic field, the moon is exposed. It's a cosmic shooting gallery, bombarded by solar particle events, SPEs, from the Sun and galactic cosmic rays, GCRs, from deep space. These high-energy particles can damage DNA, increase cancer risk, and wreak havoc on sensitive electronics. Our lunar homes cannot be flimsy tents, they must be shielded bunkers. We envision habitats buried beneath layers of regolith, perhaps even constructed within lava tubes, or built with specialized materials that absorb or deflect radiation. This constant threat compels us to develop real-time radiation monitoring, predictive models for solar flares, and robust mitigation strategies, knowledge that is absolutely critical for any extended journey beyond Earth's protective embrace. Finally, consider the subtle yet profound challenge of communication delays. Even at the speed of light, the round trip for a signal between Earth and the Moon takes approximately 2.5 seconds. This might seem minor, but it makes real-time control of robots or immediate conversations impossible. Every command, every question, every response is punctuated by a frustrating pause. For critical operations, this delay can be dangerous. This necessitates a shift towards greater autonomy for lunar robots and systems, requiring them to make complex decisions independently. It also demands sophisticated relay networks, like the proposed Lunar Gateway, a small space station orbiting the Moon. The Gateway will not only serve as a waypoint for missions, a temporary habitat for astronauts, but also as a vital communication hub, providing continuous coverage, especially to the far side where Earth is always out of view. It's a crucial node in our expanding cosmic web, extending our reach and ensuring our connection. So, how do we conquer these formidable frontiers? We do it with ingenuity, persistence, and an unwavering belief in our collective capacity to innovate. Robotics and automation will be our tireless hands and eyes, our first wave of pioneers. Before humans set foot for extended stays, robots will scout, excavate, and construct. Picture swarms of autonomous rovers equipped with sophisticated sensors and AI, mapping resources, preparing landing pads, and even 3D printing rudimentary structures. Imagine robotic arms, guided by human operators from Earth or the Gateway, meticulously assembling habitats and mining equipment. These machines will operate in environments too dangerous or tedious for humans, laying the groundwork, ensuring our safety, and maximizing our efficiency. They are the silent, tireless workers building the foundations of our lunar civilization. Central to sustainability is in situ resource utilization, ISRU, the revolutionary concept of Dassen's, quote, 47.7. Instead of hauling everything from Earth, at immense cost and effort, we will learn to use what the Moon provides, the most valuable resource: water ice. Tucked away in the permanently shadowed craters at the lunar poles, this frozen bounty is a game-changer. It's not just for drinking and agriculture. It can be electrolyzed to produce breathable oxygen for our habitats, and crucially, hydrogen and oxygen rocket propellants. The Moon could become a cosmic gas station, a fueling depot for missions venturing deeper into the solar system. Imagine launching rockets from the Moon, using lunar-derived fuel, escaping the Moon's weaker gravity well at a fraction of the energy cost of lifting off from Earth. This transforms the Moon from a mere destination into a strategic launch pad, an indispensable part of our deep space architecture. Beyond water, the very lunar regolith itself is a treasure trove. It can be melted, sintered, or 3D printed into building materials for habitats, radiation shielding, and even tools. Think of lunar bases constructed layer by robotic printers, using the local dirt to create robust radiation-resistant structures. We might even extract metals and other elements from the regolith for manufacturing, reducing our reliance on Earth and fostering a truly self-sufficient lunar economy. This is the ultimate recycling challenge, transforming barren soil into the very fabric of our new homes. To truly thrive, we must master closed-loop life support systems. On Earth, our planet's vast ecosystems endlessly recycle air, water, and waste. On the Moon, we must replicate this miracle within the confines of our habitats. Every drop of water, every breath of air, every bit of waste must be processed and reused with near-perfect efficiency. This involves advanced air filtration, water purification, and bioregenerative systems that might even include growing food in hydroponic or aeroponic farms. It's a microcosm of Earth's biosphere, meticulously engineered to sustain human life in isolation, a testament to our ability to create life where none naturally exists. And what of the human factor? Living in isolation, far from home, under constant threat, demands extraordinary psychological resilience. Astronauts will need robust support systems, opportunities for recreation, and a profound sense of purpose. The view of Earth, a swirling blue marble against the black expanse, will be a constant reminder of home, a poignant source of both inspiration and longing. Creating a sense of community, fostering teamwork, and ensuring mental well-being will be just as critical as engineering and technology. We are not just sending bodies to the Moon, we are sending minds, spirits, and the very essence of human curiosity. All these innovations, these hard-won lessons, converge on a singular, profound purpose, preparing us for Mars and beyond. Every kilogram of lunar water ice converted into rocket fuel, every regolith-printed habitat, every closed-loop system perfected, every robotic construction technique mastered, every psychological hurdle overcome. These are not just achievements for the Moon. They are the indispensable building blocks for our journey to the Red Planet. The Moon is our nearby laboratory, our accessible proving ground. It allows us to test technologies and human endurance in a relatively safe, recoverable environment, just a few days' journey away. If we can sustain life for months or years on the Moon, we can begin to envision doing the same on Mars, a planet with its own unique challenges, but also with tantalizing similarities. The Moon teaches us how to survive in an alien world, how to utilize extraterrestrial resources, how to build and operate far from Earth. It teaches us the true meaning of self-reliance in the cosmos. So when we look up at our constant companion, that silent guardian with its unwavering face, we see more than just the Moon. We see the launching pad of our future. We see the cradle of our multi-planetary destiny. We see the crucible where humanity forges its next great leap. The Moon is not merely a rock in the sky. It is the first vital step on an extraordinary journey, an invitation to embrace the universe, transforming us from an earthbound species into true citizens of the cosmos. It quietly awaits our arrival, ready to teach us the lessons we need to soar among the stars.